All right, so in this screencast, we're going to talk about significant figures. We're going to talk about what they are, where and how to identify them, and then we're also going to talk about using them in some calculations. So when we talk about significant figures, it's important to understand that all measurements that we do contain some uncertainty. Okay, every measured result, and it contains some uncertainty because it depends on the tools we use. Okay, and so the tools that we use generally in science are instruments. And so, for example, let's say you take the mass of a penny and you use these two scales. Okay, and on this scale, you get 2.53 grams for your penny. And then on this scale, you get 2.5271 grams. Okay. Um, when we look at that, we would say, hey, this scale gives us more numbers. That means that that scale maybe is more precise, right? And that's reflected in the number of digits that were given. Okay, so that would indicate to us that this scale is more precise, and maybe it's a better measurement tool than this scale. Of course, that depends on what we want to use the scales for. And so what we would say then is that this scale reports the mass to point plus or minus 0.01 grams. And this scale reports the mass to plus or minus 0.0001 grams. And so that would be the precision. And while in this example, we can look and we can say, okay, here are our two measurement tools, and we can see this is more precise, right, by the number of zeros it gives here versus here. We don't always have the measurement tools to look at when we're looking at the number. And so we have some rules to help us figure out how precise our measurement tools were. And those are our significant figure rules. So when we look at this, anytime you get numbers from a balance, right, all of those numbers are significant. Right? And those would be our significant figures. Now, when you are making a measurement with something with dashed lines, like say the temperature here, what you're going to see when we look at this, let me make this a little bigger, right? What you're going to see here when you look at this is that the number falls between 25 and 30. And so what scientists do is they estimate one digit past where the dashes are here. And so that 27, the number in red, that second digit is estimated. And while it's significant, it's called our uncertain digit. So let's do an example, okay? And before we do an example, I do want to give you a definition of significant figures. So significant figures, we talk about that definition, all digits in a number representing data or results that are known with certainty plus one uncertain digit. Right? So when we look at some examples here, what we see is that let's pretend this red line is a ribbon, right? And we're going to measure the ribbon. And we look over here and we see that we're measuring these in centimeters. And so we see the ribbon falls between 5 and 6. We would estimate between here where it falls, and we would say, okay, that's 5.4. But maybe you're looking at that and you're like, Dr. Pierce, that doesn't look like 5.4 to me. That looks like 5.5 centimeters. Maybe you're like, that doesn't look like 5.5 centimeters. That looks like 5.3 centimeters. All of these would be correct because we are estimating, and that is our uncertain digit, okay? And so when you look down here, this ruler has more divisions. And so when we look here, we have to estimate right in here. And so you may say, okay, I may say, okay, that's 5.36 centimeters. We're estimating 1 over. But you may say, no, Dr. Pierce, that's 5.38 centimeters, right? Or no, Dr. Pierce, that's 5.39 centimeters. And so maybe the burning question in your heart is, okay, Dr. Pierce, what if we had a ruler, right? And so here's our ruler, and it goes, 0, 1, 2, 3, 4, 5, and so on. And this is in centimeters. And we have our ribbon, and it comes right here, and it falls right there on that 3. How would you measure that? Well, you still have to estimate 1 digit past. So see how this ruler goes up in the ones place from 3 to 4? You would still measure here and you would say, okay, look, that's 3.0 centimeters, right? Or, if you're looking at it, you'd say 3.1 centimeters. And again, what these numbers tell us is when you look at these numbers versus these numbers, you can say, hey, this ruler is more specific than this ruler, and we can do that without having to look at the rulers. Now, let's talk about those rules. So when we don't have the measurement tool, we just have the numbers, how do we know what's significant and how do we know what's not significant? And so we have these significant figure rules. And basically, here are the rules, right? So when you're determining how many significant figures to include, you need to include all the digits known with certainty plus 1 digit that's uncertain or estimated, okay? And so when we talk about this, basically we can break things into 2 categories, either non-zero integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, or zeros, okay? And zeros are kind of our Wild West. So all non-zero integers are significant. So if you have a number that's like 1,232.7 centimeters, okay? When we look at this, all of these numbers are non-zeros, and so that means there would be 5 significant figures, and I abbreviate significant figures as SF. Now, zeros, it depends on the location. You can have leading zeros, right? And you see these in really small numbers that are decimals. That would be an example of leading zeros. You can have trailing zeros, right? Those follow a number. And then you can have captive zeros, and those are in between 2 non-zero numbers. Now, we can also have exact numbers, and these are considered to have an infinite number of significant figures. And so what you do a lot of times is you end up kind of ignoring them when it comes to significant figures. But that would be things like counted numbers, right? Where we have 32 students in a classroom or 12 eggs in a dozen, okay? And then it would be anything that's used with conversions. So any conversion factors. And we'll talk about that more when we get to conversion factors in the next screencast. So let's see how we handle zeros, okay? And of course, non-zero digits. So non-zero integers are always significant. So you can take a second right now and you can look at these 2 numbers and you can figure out how many significant figures there are. You could even pause the screencast and try on your own and then restart it. If you choose to do that, go for it. Now I'm going to continue on. So when we look at this first one, there's 3,456. All those are non-zero numbers. So we say, look, we have 4 significant figures. Okay. Then we have 7.35. All of those are non-zero numbers. We have 3 significant figures. Now, here's the big thing. Leading zeros are not significant. They are placeholders. You'll hear me say, oh, those are just placeholders. They just hold the place. They tell us to whether this goes to the 10th place, the 100th place. They're just hanging out there. So we have these leading zeros here and we ignore them. And so we go zoom by those, and well, you can do whatever you want. I like to zoom by those. And it's 392. And so there are 3 of those there. And then we zoom by those and we say, okay, there's the 4, 5, 6, and 3. So there are 4 of those there. We just ignore leading zeros. Now, trailing zeros are not significant unless they come after a decimal point. And so here, let me show you this. This guy has no decimal points. So he only has 2 significant figures. But the second that you put a decimal point right there, that makes those 2 those 2 zeros significant, because it says, hey, look, they were part of the measurement. They were given in those kind of ticks on the measuring tool, and then that's the estimated digit. So that would become 4 significant figures. And the other thing too is, even though this 0 doesn't come, right, when we say they're not unless they come they're not significant unless they come after a decimal point, that's true, but if there's a decimal point there, the decimal point, if it's after a number, if the 0's after a number and before a decimal point, it will also make those significant. Okay, so decimal points are big deals. So when we look at this, we say, okay, there's a decimal point there, so it makes that 0 significant and these 2 zeros significant as well. And so now there's 1, 2, 3, 4, 5. There are 5 significant figures. Okay. Now captive zeros are always significant. Captive zeros come between 2 numbers. So there's 4 significant figures here, or more than 2 numbers. So when we look kind of here, they could be, for example, there's a number here, there's a 0, there's a 0, there's a 0, and another number there. So you can have multiple zeros in between the 2 numbers. And so that would be 5 significant figures. Okay. Just want to see if there's anything else I want to say here before we move on. And we will... Okay, so we're going to talk about significant figures in math. And before we talk about significant figures in math, what you're going to notice is that you're going to be rounding. And so we round off in math to drop insignificant figures. Okay, so we want to drop those insignificant figures. And so when we do this, I just want to remind you of your rounding rules. For example, if you have something that's like 89.4, right, and you are rounding to 2 significant figures, you would look at this number here, and if that number is 4 or less, it stays. Okay, then this number right here stays. Okay, and so what that means then is this is now an 89. Okay, but if you have something, for example, that's 89.5, right, and you want to round to 2 significant figures, you look right here, okay, and you say, all right, that's 5 or greater, so that means that's going to round up to a 90. So that means that number there will round up to a 90. Now, when it does, if you round it up to a 90 and you don't put a decimal, that just tells us there's 1 significant figure. and you were asked to round to 2 significant figures. So you need to remember to put a decimal there, okay? I remembered what I was going to say on the previous slide. All numbers in scientific notation are significant. So what do I mean by that? Well, if you are given a number 3.729 times 10 to the fourth, and let's say that's liters, okay? When I say all numbers are significant, what I'm talking about are these numbers here, okay? Any number that's shown right here is significant. And so a lot of times what will happen is you'll get a situation where you have a number and it's like, well, I'm not happy with anything there. Okay, so you'll have a number and it looks like 3200, for example, and you need to represent that with 3 significant figures. And you're like, well, what do I do? Because you just can't drop a 0 that you lose a place. And so the best thing to do would be to take that into scientific notation where you go, okay, look, 1, 2, 3, and then you say, okay, there's 3.20 times 10 to the third. Let's make that a meters, okay? And now we've kept our places, so that's still 3,200, but we have the correct number of significant figures. And so some students like that and really lean into using scientific notation. You can, as long as I don't specify, you can use either on an exam. Now we're going to use something called the weakest link principle here with some of our numbers when we talk about, significant figures. And the number of significant figures, and basically what that means is the number of significant figures in the final result cannot be greater than the weakest link used in the calculation. Okay, now that actual rule depends on mathematical operations, which we're going to round into right now. So let's start with multiplication and division. In multiplication and division, the number of significant figures in the result equals the number of significant figures in the least precise measurement used in the calculation. So, for example, if I have 6.38 times 2.0, and I put that in my calculator, it's going to give me 12.76, okay? And I need to figure out how many significant figures that I have, because this tells me, right, I have 3 significant figures here and 2 significant figures here. And so that tells me, right, that this measuring tool measured to 2 places and this one only 1. So this is my weakest link or my least significant. And so my answer has to match that. I can't somehow just magically come up with something that's more specific. So when I look at this, I would use my rounding rules and I would round to 2 significant figures. So I look at that 7, that's greater than 5, and that would round to 13, right? Same thing with division. If you took 16.84 and you divided by 2.54, that would give you 6.6299. And so when we look at this, we say, okay, hey, look, that guy has 4 significant figures. This guy has 3 significant figures. And so that means this answer also needs 3 significant figures. And so we would say, okay, so those are our 3 significant figures. Let's look at that guy right there. That's a 9, that's greater than 5. So we're going to round up, and that would be 6.63. So use that for multiplication and division. Let's talk about addition and subtraction for just a second. In addition and subtraction, the number of significant figures in the result depends on the number of decimal places in the least accurate measurement. So now we're totally focused on decimal places. Let me highlight that. That's a kind of a big shift. Okay, so we are looking at decimal places here. So what do we mean by that? If we were to take 11.934 and add 6.8, okay, this guy has 3 decimal places. It's a very specific number. This one just has 1 decimal place. So you can say, okay, this would be the weakest link. We need to match those decimal places. Now, I like to draw a line, right, like that. And I do all my math. So when I do all my math, that gives me 18.734. And this line reminds me, hey, these are your significant figures. These you need to do the math. It needs to remind you of the rounding, but you need to make sure you drop them. And so we're going to look at that guy for rounding right there. We draw an arrow. And so when we look at that, we say, okay, that's less than 5. So it's 18.7. And that would be our answer. Do the same thing for subtraction. If we have 37.657 minus 2.1, right? I line everything up here and I say, okay, when I do this math and I put it in my calculator, it's 35.557, right? And so that's 5 or greater, so it's going to round up. And so that would give me 35.6. So that's how you do addition and subtraction. Now, maybe the question in your mind is, hey, Dr. Pierce, what happens if I have a problem where we have both addition and subtraction and division? Okay, so to determine the number of significant figures, you need to perform the individual operations to determine the number of significant figures at each step. Okay, so for example, if we look at 1.23 grams minus 0.567 grams and divided by 0.3442 centimeters cubed. Okay, let's say that's our problem, right? And the question is, well, how many significant figures do you have? So the first step involves subtracting the numerator. If it's been a minute since you've messed with numerators and denominators, the numerator's on the top and the denominator's on the bottom. Just a friendly reminder to dust off those brain cells. All right, so I'm going to come up here, right, and we're going to say, okay, let's look at that subtraction. And when we look at that subtraction, that's 1.23 grams minus 0.567 grams. Okay, so I come here, I line up my decimal places right like that, and I would say, okay, look, that's 0.663 grams. Okay, and so we look at rounding, right, and we look at this guy and we say, okay, we're gonna keep it as it is, 0.66 grams. And so there's 2 significant figures there. And because there's only 2 significant figures in the numerator, 0.66 grams, divided by 0.3442 centimeters cubed, right? So there's 2 significant figures here. And then over here, there is a bunch. So 1, 2, 3, 4, 5 significant figures. All right. So when we look at that, we end up, and we do this math, we end up with 1.924975 grams per centimeter cubed. And what we're going to do is say, okay, well, my answer needs to agree with the least because we're dividing, and that's two significant figures. So we look at the 2 right there, and we round, or we don't round, we keep it as is, 1.9 grams per centimeter cubed. Okay, so that's how you approach this. Now, as I've mentioned before, significant figures provide information about the precision associated with a given measurement. And when we talk about precision, that's just the agreement between repeated measures. It's like if you're playing darts, right? And all of the darts are really close right here. You're very precise, right? All those kind of numbers are close. Basically, another way to say this, right, is how well can you replicate a previous measurement? Right? Now, significant figures don't, however, really give us any clue into the accuracy. The accuracy is the agreement between a measured value and the accepted or true value. So, for example, if we look here, right, we see that these get pretty close to the bullseye, right? So we may say, okay, hey, look, those guys are accurate, right? And you're pretty precise. They're pretty close to each other. These are far away from the bullseye. These darts are over here, but they're all really close to each other. So we would say, hey, look, these aren't very accurate. They're not close to the true or accepted value, but they're close to each other, so they would be precise. And in this measurement, these are far apart and nowhere near the bullseye, and so these would neither be accurate or precise. Both of these are important when we are studying science and making measurements. You want your measurements to be repeatable, right? You want to, if you're measuring the mass of a penny and it's 2.5 grams or 2.2 grams, I think is what we said earlier, you want it to measure as 2.2 grams every time. You would get really frustrated if you put the penny on the scale and it was 2.2, and then the next time it was 2.5, and the next time it was 2.9. That would tell you something was wrong with your scale. Those aren't very precise measurements. So you want those to be precise. A lot of times the precision of a measurement reflects how well the measuring tool is working. But you also want it to be accurate. If you put a penny on a scale and all of a sudden it's weighing 10 pounds, that indicates probably something is wrong with your scale too. And so when we're doing science, we want these to be accurate, our numbers to be accurate and precise.